Hi, welcome to today's lecture on quantitative demand analysis. So once again, I would recommend taking the topics that we're going over each week and run them through Google. And if you do that for this week, the main topic is actually elasticity. And you'll find that there's been lots in the news recently about elasticity. For example, this article from a fairly recent retail publication on Home Depot and Walmart having to revisit their models for measuring elasticity given shifts in the demand curve, given the tariffs that have been recently imposed. So that affects a lot of what's happening in the retail as well as the manufacturing industry. You may also recall that the price of eggs spiked this past year to pretty much outrageous levels, but not surprisingly, there's not a lot of price sensitivity to eggs. And so the egg producers still did extremely well, and it didn't reduce the demand enough to lower their overall revenue. So once again, price elasticity is a great concept. It's really an extension of what we did in the previous lecture on supply and demand, measuring the sensitivity of the quantity demanded given changes in the price. And so that's the main topic for this week. We're going to talk about elasticity, how it's measured, and how to use it, and then basically how to use all of these tools in forecasting what might happen given shifts in supply, demand, prices, and quantities. So elasticity is an economic concept about the how much one variable will respond given changes in another variable. It's a percentage measure. It's not exactly the slope of a line, say a demand or a supply curve, but the slope, the derivative, is used in calculating it. We have to make some adjustments to get to a percentage so that we know that, for example, if the price of something increases by 1%, we want to know the percentage impact on the quantity that's demanded. So the example that they use in the book is the number of hours of studying and the relationship to a student's grade performance. So we're going to use the data. We're going to use the example in the book, but I'm actually going to put some numbers to it. They didn't do the numbers, and I think it's easier to really understand what's going on if we just actually plug in some data. And so let's assume that we've done some economic modeling based upon prior classes. We have not, by the way. This is entirely fictitious data that we're using. But let's say that a student's grade is basically 60 plus 4 times the number of hours that they study minus 0.05 times the number of hours that they study squared. That's basically diminishing returns. So while generally the more you study, the better off you're going to do, at some point, each additional hour of study is not going to add as much incremental knowledge. Again, don't try and apply this model to your individual studies. That's going to depend on what how quickly you learn, how familiar this information is, how recently you took an undergraduate economics course, and those sorts of things, whether you are applying this on your job. So this is totally fictitious. Don't use this model for anything other than understanding how we compute elasticities. That's the purpose of this example. And so basically, that's our model. So this is how it would look if we actually graphed it. So we have the number of study hours on the right-hand side, and we have grades on the left-hand axis instead of prices here. We're relating grades to the number of hours studied. And so, for example, if we don't do any studying, if S is 0, then we can expect to get about a 60%. If we study 5 hours a week, we'd expect to get about an 80%. And if we study 10 hours a week, we would expect something around a 95%. Obviously, we really can't go above 100, but mathematically, that's what the formula shows us. So what we want to do is we want to measure the sensitivity to the grades relative to a change in study hours. So elasticity of G with respect to S is the percentage change in the grade relative to the percentage change in the number of study hours. So we could measure this after the fact, of course, and just take the percentage of one over the percentage of other. We're going to come back and do that using a different example later. We call that the arc elasticity. But mathematically, given the formula, we should be able to determine what this elasticity measure should be. And so basically the formula is that elasticity of G relative to S should be the derivative of G relative to S. So remember, that's the slope of the line. The derivative of G relative to S would be the slope of that line, the relationship. But then we have to scale it in order to get a percentage. So then we're going to take S, the number of hours of study, divided by G, the grade. And by multiplying these two together, we're going to get the elasticity of grades relative to the number of study hours. So that, again, that first term in the equation is the derivative of G with respect to S. How much G changes for a very small change in S. Recall we did that in the very first lecture in week 1. And the second term basically scales that rate of change and puts it in percentage terms. So if we look at 10 hours of study, if we work through the formula, we would get a grade of 95. So we want to know at this particular point in time, what is the derivative of G with respect to S? So recall from a derivative, when we take the derivative of this formula, the coefficient just drops out because it's not affected by a change in S. It's 60 regardless. So that's not affected by a change of S. The 4S, when we take the derivative, the S simply drops off, so we have a 4. And the S squared, basically we take the 2, move it to the front. 2 times 0.05 gives us 0.1 S. So the derivative of G with respect to S is 4 minus 0.1 S, S being 10. So we basically have the derivative of G with respect to S is 3. And then we take the ratio of the number of study hours divided by the grade, which is 95, and we get a ratio of 0.1053. So elasticity is the derivative of 3 times the scaling factor, S over G, and that gives us an elasticity of 0.316. So basically, what elasticity tells you, if you have a certain percentage increase in study time, what's likely to be the percentage increase in grade. So for a 10% increase in study time, we multiply that by 0.316, we would get a 3.16% increase in the grade, which would take the grade from 95 to about 98. So while the study hours are increasing 10%, the grade is only increasing by 3%, but we were already at a fairly high grade already, so the elasticity is not that large in this particular example, okay? Another way of thinking about it is that, remember, the derivative of G with respect to S is 3, so basically a 10% increase in study time here would be 1 hour. So you're starting with 10. You study 1 more hour, it's going to increase your grade by about 3 points, from 95 to 98. The elasticity gives us a way, on percentage terms, of evaluating how much G is going to change with respect to S given a given percentage change in S. And we can do this for any variables. So a couple of things to know that are important. One is the sign of the relationship. So if it's a positive elasticity, that means an increase in S leads to an increase in G, or whatever other variables we're using. If it's negative, then an increase in S leads to a decrease in G, which is not the case in this particular example. And then we also want to know the absolute value of that number. If the absolute value is greater than 1, that means it's very elastic. It means that G is highly responsive to changes in S. If the absolute value is less than 1, then it's slightly responsive. So let's go back here. First, we have a positive number, so they're positively related. An increase in studying does lead to an increase in grades. And we have the absolute value is less than 1. So we have a fairly modest elasticity. A 10% increase in study time equates to about a 3% increase in grades. Elasticity of 1 would mean that a 10% increase in grades would lead to a 10% increase in study hours. So again, if we have a elasticity of greater than 1, then it's highly responsive. If it is less than 1, then it's slightly responsive. If it's exactly to 1, then they respond equally. A 10% increase in one results in a 10% increase in the other. So we can measure elasticity between lots of different variables. The first and probably the most important is calculating a product's own price elasticity. What that means is the relationship between the price of a product and the demand for that same product. We call that the own price elasticity of demand. So what we want to know is the elasticity of the quantity demanded relative to the price. So the numerator is the percentage change in the quantity demanded relative to the percentage change in the price. And this, again, is the same product. It's quantity of X and the price of X. By definition, we should have a negative number because of the law of demand. The higher the price, the fewer units that should be demanded. The magnitude, we take the absolute value. If it's greater than 1, then we call it elastic. If it's less than 1, we call it inelastic. It moves, but not to as big an amount. And if it's equal to 1, we call that unitary elasticity. So let's put some numbers to it. So this is data from your book, table 3-1, where we measure total revenue for a company that's making software. And we have basically the demand equation here, where the quantity demanded is equal to 80 minus 2 times the price of X. So we've got the price here, we've got the quantity that would be sold at those prices, and then we've got already computed for you here the own price elasticity. All right. And then over here, we have the total revenue. So for example, $5 per unit times 70 units is $350. $10 per unit times 60 is 600, etc. So the way this negative 0.14 is calculated is if we look at this formula, we take the derivative, the coefficient just drops off. The derivative of minus 2p is a minus 2, so the p drops off. And so we take 2 times the price divided by the quantity, we get a negative 0.14. So that's a relatively small amount of elasticity. If we raise the price from $5 up to $10, we're going to get a slight reduction in the quantity demanded because it's very low elasticity. But notice as we increase the price from there, elasticity gets bigger and bigger. Okay, so by the time we get to a price of 20 and a quantity sold of 40, we have price elasticity of -1. So then we have unitary elasticity. And then once we get over that level, then there's even more and more of an impact. So the more and more that we raise prices, the more it's going to reduce demand. There's a slight effect here, it's inelastic. Then we have up here, once it gets past this level, we have a very elastic response. Okay, so the higher the elasticity, the lower the quantity demanded is going to drop. Okay, and if you do this calculation, I just did it here for B to show you, but if you calculate it for all of these, the derivative is 2, so the slope of the line doesn't change. But multiplying by the price divided by the quantity does change, and so that's why the overall elasticity is changing. So the other thing we want to make sure we make note of here is this total revenue column. Okay, as we're increasing our prices, the quantity that we're selling is declining. But when we take the price times the quantity to get the total revenue, what we notice is from moving from A up to E, as we're increasing the prices, the quantity is declining, but our total revenue is actually increasing. Okay, that's because the quantity is not declining all that much relative to the increase in price. So we're actually increasing or maximizing our total revenue up to this point E, where we have unitary elasticity. After that point, any additional increases in the price are going to reduce the quantity sold by a large percentage amount. And so our total revenue is going to go down. So the point at which we reach unitary elasticity is going to be the point at which we maximize our revenue. Okay? If we look at this graphically, oops, went the wrong direction. If we look at this graphically, and we're showing A through E here, so going from A to E as the prices are increasing, so the letters are going backwards, but that's okay. So from A to E, as we raise the prices, our profits are increasing, but once we get past E, our profits start to decrease. So our maximum revenue, maximum revenue is the point at which we reach that unitary elasticity. We talk often about perfectly elastic or inelastic products. They don't really exist, but just so you know the terms, perfectly elastic, there would be no change in price given increases in demand, and perfectly inelastic, the price can change and it wouldn't change demand. The way to remember which is elastic and which is inelastic is think of this bar in the middle as the middle bar and an E. So that's sort of part of an E is perfectly elastic, and then perfectly inelastic looks like an I in inelastic. Again, we're not going to see products to that extreme. It's theoretical, just good to know that terminology. Okay, so what factors can influence the price elasticity for a product's own price? So the availability and number of substitutes. The more substitutes that there are, the more elastic it's going to be, the more that the quantity is going to change given a change in price. The time horizon, the more time customers have to react, the more elastic it's going to be. That gives them time to change to another product if they need to. And it also depends upon how big of an item this is in terms of a consumer's budget. If it's a very small item, the book uses pepper, I think, as the example, where we don't spend very much on pepper, so we're not all that price sensitive to pepper. But if it's a large share of our budget, so if you are in a country that eats a lot of rice, it's a much bigger share of your budget, your food budget, than pepper. And so rice is going to be much more elastic than, say, pepper. So as we mentioned earlier, there is a relationship between where the maximum revenue is, which is where we reach that unitary elasticity. We can also calculate the marginal revenue. So remember that from chapter 1. We want to find the marginal revenue, and in particular, we want to maximize the marginal revenue minus the marginal cost. Well, we can actually use elasticity to approximate what our marginal revenue is. It's equal to the price times 1 plus E over E, where E is elasticity. And that will give us an estimate of our marginal revenue. So in the previous examples, we had a formal formula that we had to determine what the quantity demanded was given a particular price. We don't always have all that data to do it, but it's actually fairly easy to do by just getting a couple of data points. And the reason it's called arc elasticity, and the reason is that you're basically think of that curve that's an arc, and we're just going to take 2 points. And based upon those 2 points, we're going to estimate what the elasticity is for this particular product. So remember, this again is own elasticity. It's the elasticity of the quantity demanded relative to the price for our own product. So let's say we have a cafe, maybe a couple of cafes, and initially we're charging $4.50 for a cup of coffee, and we're selling about 1,000 cups in a week. And then we decide that we're going to lower our price. We lower our price to $4 a cup, and our weekly sales increase to 1,250 cups because, again, we lowered our price, so the quantity demanded goes up. We can actually use that data to estimate the elasticity of demand between these 2 points. So we basically can take the percentage change in the quantity and the percentage change in price and divide the percentage change in quantity by the percentage change in price. And that gives us an estimate of the elasticity. So if we look at the change in quantity, we went from 1,250, we went from 1,000 to 1,250. So we had an increase in the quantity divided by the average of those 2 points gives us 0.22 or 22%. The change in price went from $4.50 down to $4. The average price was $4.25. So we had a price decline 11.76%. So we take the 0.22, the change in quantity on a percentage basis, divided by the change in price on a percentage basis, and we get a negative 1.89. So what does that mean? That basically means for every 1% change in price, that the quantity is going to go up or down by about 1.89 times. That's very elastic. So it's above 1, so it's very elastic. It's negative because this is our own price elasticity. So we can use that going forward to evaluate further price changes, whether they're up or down. We can estimate in advance what would likely happen to our weekly sales of coffee. So again, in this case, the elasticity, the absolute value is greater than 1, so we're highly responsive to price changes. A 1% price decrease leads to a 1.89% increase in quantity. Similarly, a 1% price increase would lead to about a 2% decrease in quantity demanded. So in this case, lowering price actually increases our total revenue, which we can calculate very simply. So before, we were selling 1,000 cups at $4.50. Our total revenue was $4,500. Now we're selling 1,250 cups at $4. Our total revenue went up to $5,000, an increase of $500. So that was own price elasticity. Now we're going to turn to cross price elasticity. So this is when we look at how changes in prices of other products affect the quantity demanded of our product. So in this case, the elasticity of the quantity demanded of X, X being our product, relative to a price of Y, which is another product. Okay. If this elasticity is positive, then that means that X and Y are substitutes. So again, I'll use General Motors versus, I think I used Toyota earlier. If the price of Toyota goes up, then people may buy more, a higher quantity of American-made cars. I guess Toyotas are also made in America, so that's a bad example. But the brand, they may buy a different brand. Price of Toyota goes up, then they may buy something from General Motors. So those are substitutes. If it's a negative relationship, then X and Y are complements. So this is the estimate of the cross elasticity of demand of minus 0.18. So if we expect that food is going to increase by 10, food cost is going to increase by 10%, then people will have less money to spend on clothing. So we would expect the demand for clothing to decline by the elasticity, minus 1.8 times 10%, or in this case, 1.8%. We can also calculate a formula for determining what the overall change in revenue is from a price change for one firm if we sell more than one goods. More than one type of product. So in this case, we have the revenue from X and the revenue from Y, and we can calculate what our total revenue is. It's actually, the formula looks intimidating, but it's not all that complicated. So we're going to put some numbers to this. I think it's a little easier to understand. So we run a restaurant. We make revenues from selling hamburgers, and we also make revenues from selling soda, about $4,000 a week from hamburgers and about $2,000 a week from soda sales. We have our own price elasticity for burgers. That's a negative 1.5. So that means as we increase the price of hamburgers, the quantity demanded of hamburgers is going to go down. Our revenue overall may go up, though, depending upon how much the change is. In this case, it's fairly elastic. Its own elasticity, so it's negative. And then we also have the cross elasticity of demand between sodas and hamburgers, which is a negative 4.0. So what that means is that these are complements as opposed to substitutes. So they're going to move in the same direction. So we have the impact here is if we raise the price of hamburgers, we want to know what the impact is on the quantity of sodas that is sold. Okay, so remember here, we're just looking at hamburgers. We're going to increase the price of hamburgers by 1%. And what we want to estimate is what's going to happen to our overall revenue if we do that. Our overall revenue is going to go down depending upon the change in quantity, or are they going to increase? So we're going to take and apply the formula. We have the level of revenues. We're going to use the elasticity, own elasticity of hamburgers here. We're going to use the elasticity of the sodas relative to hamburgers here. And if we run through that calculation, we're going to get a change of revenues of a positive $100. So if we actually sort of break that down and just work through what's going to happen is we're going to end up selling, we're reducing the price of hamburgers by 1%. We're going to sell 1.5% more burgers, but at a slightly lower price. our burger revenue is actually going to go up by $20. But more importantly, the elasticity is very high for sodas. So by decreasing our price of hamburgers by 1%, we're going to sell a lot more soda. So we sell 4% more soda, and our soda revenue goes up by $80. So overall, our revenue goes up for burgers, our revenue goes up even more for sodas, and we actually increased our revenue by $100 by reducing the price of hamburgers for these particular products. So we can also calculate income elasticity. So we can look at how the change in quantity demanded changes for a change in income levels. So remember here, we can have a positive or a negative relationship. If it's a normal good, then an increase in income is going to increase the quantity that's demanded. If it's an inferior good, McDonald's was the example I used earlier, then with an increase in income, people may go to higher end restaurants. And so there may be a lower amount that's actually demanded. So in previously, when we were talking about supply and demand, we were just looking at the quantity demanded itself. Here we're measuring elasticity, which is the percentage change in the quantity demanded relative to a percentage change in income. So the example here is organic potatoes. And so someone's already measured for us what the income elasticity of demand is for organic potatoes, and it's 2.16. So we know that, first of all, that's a positive number. So that tells us that this is a normal good because an increase in income is going to raise the demand for organic potatoes. The fact that the absolute value is greater than 1 means this is actually a very elastic relationship. And so what happens if income is projected to actually decrease by 10%? Well, because this is a normal good, we would expect the quantity demanded of organic potatoes would decline. But how do we calculate the percent? We're going to work backwards. So we have the elasticity of 2.26. We have the minus 10% change in income levels. So the percentage change in demand is the only thing missing. We solve backwards and we find out that the demand for organic potatoes would actually decline by 22.6%. So quite sensitive to a decline of 10% in income levels. We can do the same thing for advertising and any other factor that affects the demand. Anything in our demand formula, we can calculate the price elasticities of, so we can see what the overall impact is for a change on the quantity demanded of a particular product. So recall the demand function. We can algebraically express the quantity that's demanded based upon various factors. In this case, we have our own product. We have another product that might be a substitute. It might be a complement, hamburgers and soda versus different types of cars. You have the income levels. This could be positive or negative, depending on whether it's a normal good or an inferior good. And then you've got other factors such as advertising, et cetera. And we're just going to denote those H. That's sort of the generic formula. Let's put some meat on that. So let's do a calculation. So let's say that we're a shoe company and we're producing a particular shoe, the invigorated ped shoes. And they typically sell for $25 a pair. But there's another shoe that people could buy. We'll just call that Y, and it sells for $35 a pair. We're going to do some advertising for our shoe, and we know the level of consumer income. Our finance quantitative department has calculated a formula for us on the quantity demanded as a function of these variables. It's 100 minus 3px plus 4p minus 0.01 plus 2a. So a few things to notice here. We have a negative relationship here, which is what we would expect because of the law of demand. The higher the price of our shoes, the less the amount would be demanded. So that's a negative relationship. In this case, we have a positive coefficient here on this shoe, which also makes sense because these are substitutes. So if the price of this other shoe goes up, people will demand more of our shoe. Price goes down, people will buy it and not buy our shoe, perhaps. We have a relationship here of a negative coefficient for the level of income. That tells us that this is an inferior good. It means as people's income increases, they are going to buy fewer of our shoes. So maybe ours is a low quality shoe, and that's why it's selling for $25, while the other one is higher quality and is selling for $35. So as people have more income, they're going to buy the higher quality shoe, even though ours are cheaper. So we have a negative relationship here. If this were a normal good, this would be a positive relationship. We have a positive coefficient on advertising. So this shows us that for our product, the more we spend on advertising, the more we should sell. We want to hold things constant other than the price and the quantity for our good. So we're going to plug in all of these things into the formula. And the ideal quantity at this price that we would produce would be 65 units. At a price of $25 a pair, 35 for Y, at that income level and that level of advertising, then in theory, the quantity demanded should be 65 units. We can then calculate the price elasticity of our own product, of the other product, of income, and even of advertising, okay? And we do that by looking at the derivatives. So remember, the elasticity formula is the derivative times a ratio. And that gives us, in this case, you basically plug in the numbers. Remember the derivatives, we don't have any squares here, so the things just drop off. So the derivative of 3p would be 3, 4p, etc. And so we can calculate the elasticity. So we've got our own price elasticity of minus 1.5. We have a cross price elasticity of plus 2.5. And we have an income elasticity of a minus 3.08. So all of these, the absolute value is greater than 1. So it's a pretty strong relationship. Our own is negative as we expect. Income is negative because we're an inferior good. And this good is a substitute because the more its price increases, the more people are going to buy of our particular shoe. So again, those are the conclusions. Own price elasticity is negative, which is expected. Absolute value is greater than 1, so very elastic. The cross elasticity is positive, so these products are substitutes. And the income elasticity is negative. So we can determine for each of these factors, if any one of them were to change by a percentage, we can calculate what the percentage change is on our overall quantity. So for example, holding everything equal, if our own price increases by 1%, the quantity demanded would decline by 1.15%. If the price of this good increases by 1%, then they should demand 2% more of our goods. If income increases by 1%, then our quantity demanded would go down by 3%. So we don't have to recalculate for every level of all of these variables. We know in advance what the percentage change in quantity demanded is likely to be given a change in any one or perhaps all of those variables. So elasticity, I know it sounds a little complicated, but we're basically using the same supply and demand information we did before. We're using the data to calculate the percentage change in responsiveness to one variable over another. The most important being our own price elasticity. That's going to tell us if we raise our prices, what's going to happen to overall revenue. And if we decrease our prices, what's going to happen to overall revenue. Arc elasticity is a shortcut. to doing any fancy derivative calculations, to just take 2 points and estimate what the price elasticity is for a particular product. Calculating the elasticity helps us identify which products are substitutes versus complements, and it helps us distinguish between normal goods versus inferior goods. Overall, this elasticity gives us a quick way of calculating what the impact of different decisions we may make, or different decisions our competitors may make, or what happens when income levels increase for the population. So all of these can be used to give a quick estimate of what the impact is going to be on the quantity demanded for our particular product, which we can then use in pricing and production decisions. So thank you, and have a great rest of your week.